Hello, this is Mrs. Tackett, and I want to talk to you today about how the formula sheet and the Desmos calculators can help you pass the geometry end of course assessment. So we're going to look at some problems that the formula sheet should be your guide and should be your first go-to. For instance, here is a formula. It's asking for the area in meters. It's given us information in feet and inches. So what could the formula sheet do to help me? Well, let's take a look. You will have this both as a printed copy and as a handout. Notice the top section has conversions, and down here we get the area of a parallelogram. So we see that our shape in our problem fits that relatively nearly of a parallelogram. So I'm going to pull that formula out. Now, one thing I know is I can't multiply feet and inches, and I need my answer to be in meters. So I recall that when I first looked at this formula sheet, up at the very top, it gave me some conversions that I can use. For instance, I can convert the 10 feet into inches and the inches into meters. So I can go 10 feet all over 1 times 12 inches all over 1 foot times 1 meter all over 39.37 inches. Notice what's happening. The inches in the denominator cancel out the inches in the numerator, the feet in the denominator cancel out the feet in the numerator. I can do the same for this 400 inches. And I'm just going to multiply that by 1 meter over 39.37 inches. The inches in the numerator and denominator again cancel out. Notice that if this has a right angle, this is my height, this is my base. So now I can use my Desmos calculator to solve this problem. And notice too that I'm not leaving things in their own, I'm not using my tabs the way we sometimes do, which is piling them up. I'm separating this out. So I know that my formula is base times height, and I can literally key in 10 divided by 1 times 12 divided by 1 times 1 divided by 39.37 and parentheses times parentheses 400 divided by 1 times 1 divided by 39.37 in parentheses. So now I have the area based on my diagonal analysis. There was a calculation error there. I just simply went in and corrected it. So by using the formula sheet, I was able to convert my problem by using the Desmos calculator. I input those conversions that I lined up and came up with a value. It's asking me for how many meters, so I can round to the nearest whole and say 31 meters squared as my answer. So again, using the calculation sheet to get my conversions, using the Desmos, we can successfully solve this problem. Another type of problem is the trigonometry problem. Now, one of the things you do need to know is how to label a triangle. So when we do this, we have an angle of reference. From that angle of reference, x is the opposite side. Across from the right angle is the hypotenuse. Next to the angle is the adjacent side. I'm selecting these due to the reference angle. Now, if I look at my formula sheet, they give me the trig functions. And I can see that if I'm solving for x, I want to use the sine of the angle I'm given, opposite over hypotenuse, because I'm given the hypotenuse. That's what's driving me to that sine function, is what I was given. So I can solve this using trigonometry, and I now know how to set this up. 30 or sine of 30 all over 1 equals the opposite, my unknown, all over 100. You should understand cross multiply and divide. So again, this is just part of the setup of this problem. And I get 100 times sine 30. And that will, when I put that into a calculator, it's going to give me x. So now I come to my Desmos calculator. I can double check that it's in degrees. The testing calculator does default to degrees. Some of the other ones do not. But I want to make sure it's in degrees. We are not working in radian mode. Now I just type it in exactly as I've written it. 100 times the function is the sine function, 30 degrees. To give me that is 50. So when we're given a side and an angle of a right triangle, normally we will use trigonometric functions. I could have solved this using the other item that was given to me in the right triangle, or the trigonometric functions portion, and that's the fact that I have a 30, 60, 90 degree triangle. We know this other degree is 60 degrees because the interior angles of a triangle always add up to 180 degrees. And that has a relationship that we can use, and that can really help us out. For instance, in finding y, if they ask us to find y in radical form, this is going to be our best way to do this. Because watch, if I label this triangle, the y is going to have the relationship of x square root of 3. X is going to be x, and the hypotenuse will be 2x, according to the labeling that I'm given right here. Notice I matched it up with the 30-degree angle. We can see that that works because if the hypotenuse is 2x, then x does have to be 50, which is what we got when we used trigonometry. So you could have used this to solve that problem as well. Let's look at finding the adjacent side now. The adjacent side is x, which we know is 50, times the square root of 3. So if we have to leave it in radical form, we're in radical form. You could say, but I could use the Pythagorean theorem. And you could. Which says a squared plus b squared equals c squared. We did have to find one of these sides using either of these two methods. Now we can say that 50 squared plus y squared equals 100 squared. Notice we're naming the sides across from the angles. So that means our y equals the square root of 100 squared minus 50 squared. Easy enough to put into Desmos. But notice we have this 86.6. If they asked for radical form, if we had gotten a full integer like the 50, that would have been good. But we now have to solve for this a little bit more, because if they ask for it in radical form, they want a whole integer, and anything that's not an integer left under the radical. So we can take a step back and find out what 100 squared minus 50 squared is, and we can solve it this way. Well, 75,000, I know 25 goes into 75,000, and 25 is a perfect square, so that would give me two sets of 5s. I think 300 is divisible by 25. And then 12, I know, has the values of 4 and 3, and 4 is a perfect square. So I can still get to that 50 square root of 3 this way, using the Pythagorean theorem and rationalizing the radical. I've got two factors of 25 to take out. So outside the radical, I'm going to put 25. 4 has two factors of 2, and the 3 stays under the radical. It's a prime number. Notice I'm still getting 50 square root of 3, but I had to do more work for it using the Pythagorean theorem. If we use our formula sheet for the 45, 45, 90 or 30, 60, 90 triangles, we may save ourselves some work. Here we have an angle of elevation, meaning we have a horizontal and this plane is taking off, and the angle from the ground up is what we call an angle of elevation. And for some reason, maybe they want us to find this. Because I have sides and two sides and an angle, I need to use trigonometry. So I'm going to label things in a way that will help me with that. The hypotenuse, remember, is always across from the right angle. The opposite side is across from the angle of reference. And the adjacent side is next to the angle of reference. The angle of reference being A, that's where our unknown is. Again, once I label my triangle, I can come back here into my formula sheet. And now with my sides labeled, I can see, oh, I need the tangent because that involves the two values I have, the opposite side and the adjacent side. Now to do the tangent, we don't have the angle. So what we have to do is use the inverse tangent. And if I write that out, you learned inverse functions in algebra. You're working with that perhaps even now. I'm still going to go the 300 over the 400. I need my calculator to solve that. But because I'm looking at the angle, remember, I'm looking at an inverse function. So I'm still going to go to functions, trig, but now look, I'm picking that -1. Remember, inverse functions raise to that -1 power. I just key in my relationship of opposite to adjacent, and I might want to still make sure that I'm in degrees, just as a double check. And it's either going to ask me for whole degrees or degrees rounded to the nearest tenth. In this case, I can't use any of the 45, 60, 45, 45, 90 triangles or 60, 30 triangles. So I'm either going to write 37 degrees or 36.9 degrees, depending on what they ask me to round it to. So ways that formula sheet is helping us out if we know how to label our triangles. The formula sheet can help us with surface area and volume. To find surface area, we basically have to find each shape's area, right? We might know the surface area formula. 2 base plus the perimeter times the height. But if you don't, we can find the area of each of these spaces. The formula sheet is going to help us out. This is a triangular prism. Triangular because the base is a triangle. So I need the formula for a triangle. And notice the big B is the base of the area. So this is just asking for the small b. We do have to align things. We're given the 10 of this base. We are allowed to assume that this is also 10 centimeters. I have my height. My height is always dropped from a vertex with a right angle. So for my base, I'm going to have half times 10 times 8.3, or 83. No, 8.3. There's a decimal point there. There's two bases, so whatever I do, I'll multiply that by 2. Notice these sides are equal rectangles. They have a width of 10 and a height of 14. So now I can go to my formula sheet, get my parallelogram formula, and we said our base was 10, our height was 14, and because this had a triangle, we're going to multiply that by 3. We simply need to add all these up. So now I pull up my Desmos calculator. And into Desmos, I literally key in what I just wrote. Of course, you could eliminate the half and the 2. I'm just putting it in exactly as I wrote it. 10 times 8.3, and my parentheses, plus the 3, and I think I need to put a times sign. I don't think it does. Ten times 14. And that's giving me a surface area of 503. So by recognizing the shapes, I can use my formula sheet and do surface area, even if I forget the surface area formula. Just breaking those shapes down one at a time, and that was centimeters squared. The volume of prisms is also here. A general prism, base times height. We found the area of the base when we found the area of a triangle. So half 10 times 8.3. We did multiply that by 2. So we will have to do that again, and we're going to multiply by the height, which is the distance between those two bases, of 14. So we're going to do 1 times base of the triangle times the 8.3 height. Now that's the base, the big B, and then times the height, the distance between the two triangles, of 14, to get 581. And that's going to be centimeters cubed because we're dealing with volume, and volume is always cubed. So again, we use the formula sheet and input our work into Desmos, trying to avoid rounding as much as possible. Let's look at something else. What if you had to find the surface area of this cone and you're like, oh, cone, I forget. And notice, again, they're not giving us surface area. But again, with a little creative thought, we can see that a cone is really kind of triangular. And what's making our base? Well, isn't that the unfolding of the circumference? And we have the height. So if we know the circumference, we can find the surface area of this cone. Because I bet our formula sheet has the area of a triangle, and it does. And it has the circumference of a circle. So we can pull our formula over to our sheet. And again, I'm just using this to copy and paste. And we'll need that area of the circle next because that's the other base, right? So our surface area is going to include the circumference, which is 2 pi r, and I'm going to leave it in pi. I can multiply by pi later. So that equals 2 pi, and it's 2 meters, or 4 pi. That's my base. I bring that up here, half times 4, that's my base, times the 6 of my height, and that's 4 pi. So that equals 12 pi meters. Now I need the area of the base in order to complete the surface area. And that just equals pi r squared, so pi 2 squared, or 4 pi, 16 pi meters squared. That would be my surface area. If they wanted pi, they might tell me that pi equals 3.14, in which case I would multiply by 3.14. If they don't, then I would probably choose to use the pi button on my calculator. So 16 times pi to get 50.3. So that's my surface area. Volume, they give us the volume of a cone. So if I come down here, we pull out our volume formula, and now we just have to follow it. And if they tell us to leave it in pi, we've got it even simpler. We do have a little complication in the sense that we do not have the height. This 6 was not the height of the cone, it was what we call the slant height. We need this height. And to find that, we're going to use the Pythagorean theorem. This you have to know. They do not put it out there for you. Notice that our right angles here, our height is the difference of the hypotenuse squared minus the side squared, and the square root of that difference. Getting my handy dandy calculator out here. I see that my height is 5.66. So now I just go 1/3 pi 2 squared, 2 is still our radius, times 5.66. If I wanted to avoid a rounding error, I might even continue here . So times, and maybe they don't tell us to do it in pi, so I'm going to do pi 2 squared times 1/3. And that way I'm letting the calculator do more and more of the work for me to give me that volume of the cone. And I'm going to double check. Yes, I included the 1/3. Here's my pi, here's my r, here's my height. And if they tell me to round, maybe to the nearest tenth, I can say 23.7 meters cubed. They tell me to leave it in terms of pi. I just leave the pi out of here and express it in terms of pi. Putting the pi there. So the area formulas are out there. The volume formulas are out there. Surface area formulas are not, so you may have to get a little creative in taking your figure apart. What about finding the perimeter of a quadrilateral? Well, the formula sheet doesn't have anything about perimeter, but what can help us here is the Desmos calculator, because maybe we can cut down some of this work. And the other thing that the formula sheet does give us is the distance formula, and we're going to need it. So one of the things that I can do is graph points on Desmos. So let me just put those out there. -1, 4, 4, 4, 3, -2. And noticing I'm labeling them because that's going to help me overall. -1, -4. Now that I've got them graphed, I noticed that, wow, I don't have to do as much math as I thought I had to do. I can do the ruler postulate, or I can count here and here, right? -1, 4, 4, 4. But I'm going to have to use the distance formula here and here. So by graphing, I got some information. Now, just to show you that Desmos does absolute value, I am going to take and find the distance, -1 minus 4, which is 5 between these two, and 4 minus a -4 for those two. Now I have to use the distance formula. This year they put the distance formula onto our spreadsheet here, onto our formula sheet. So now I have something I can use, and I just need to fill in. I'm going to work with the 4.4 and the 3.2 and put it into Desmos. The distance formula is telling me the difference in the x values. So 4 minus 3, quantity squared, plus 4 minus a -2. Quantity squared. And now I have to find the distance between these two. Again, do another square root. 3 minus a -1. Quantity squared. Plus -2 minus a -4. Notice I'm not putting negatives in. I'm just putting in the minus sign twice. That's just how Desmos works. Now I just come down here. 5 plus 8 plus 6.08 plus 4.47 to get 22.55. Again, it made it a little bit easier seeing those points already up there and working from a graph than just plugging in the distance formula right off the bat to get me where I need it to be. So use the formula sheet. That's where we got the distance formula. Use the Desmos calculator. Let it do some of your handiwork for you. And we found our perimeter. And it depends on where they wanted it rounded to. It could be 23 units, or it could be 22.6 units. We just would have to know what to round it to. Probability. We don't get much with probability. But here we have, let's read the problem and see if the formula sheet can help us out. The probability that a registered voter is female is 0.5. The probability that a registered voter is registered as an independent is 0.3. The probability that a registered voter is female and is registered as independent is 0.2. So we're to find the probability that a registered voter is female and independent. What might help if I just put this in kind of probability terms. P of F equals 0.5. P independent equals 0.3. P, F, and I equals 0.2. You may or may not remember how to do that. No problem. Now let me see if the formula sheet will help me at all. Well, they do have something about probability. And isn't the word or used here? I bet I could use that addition formula. And it might help me out. And now that I've kind of put things in probability terms, maybe it's just the ticket. So I'm going to go and say, okay, this is P of F or P of I. Ah, now that makes sense because I can change this with an F, this with an I, this with an F, and I. Now it's just a matter of filling in my numbers. 0.5 plus 0.3 minus 0.2. That's 0.8 tenths minus 6 tenths. Sorry, minus 2 tenths is 6 tenths. So the probability is 6 tenths, or 60%. Again, look, this rule exists. It's on the sheet. Obviously, they're going to ask a question that will probably use it. Look for the word or. Then you may need to use this sheet, this formula. Is the only probability formula on the sheet. We know that Desmos plots points, but can it help us if we're given these 2 points, find the equation of a line? Well, let's see what we can gain from Desmos, what it will do for us. So I have a point, 4, 8, plot it and label it. And I have a point, -6, 4, and I'm going to label that. Well, if I have to give the slope, you know what? Maybe I could do something with that, right? Because isn't a line can be drawn between any 2 points, so maybe if I count up 1, 2, 3, 4, 5, or sorry, 1, 2, 3, 4, and I go over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it looks like my slope, if I'm counting it out after plotting these, is 4/10. Now I know I can reduce that because there's a factor of 2 in the numerator and denominator to 2/5. So I've got part of my line right there. I could, if I know my formulas, say y equals, and then we know we want to see mx plus b, or maybe you don't. This is what they call the slope-intercept form of a line that they may ask you to write. This slope could help you with parallel or perpendicular, since a parallel line will have the same slope. You could plot the points of a quadrilateral and check the slope on each side. A perpendicular slope will be opposite sign, so negative, and inverted. So you could see if they had right angles. To write in this form, I need a y-intercept. So I could get pretty close. Maybe not perfectly, by kind of drawing out a line through here, right? And I see that it's going to cross 6, so I'd be pretty close if I did say something like y equals 2/5 x plus 6. Another way I could get there is there's the point slope formula. Not saying that's correct, I'm just saying that's close. So if you know the point slope formula, again, you're not given these, but you are learning them if you're taking algebra. I can literally type my equation in, and I can select either of these points to be my x1, y1. And I can key it in exactly as I wrote it right there. Since I know my slope, I'm going to go y minus my y point value is 8, and I can go equal two-fifths parentheses x minus the x value of 4. And then all I have to do is click, and I see that, yeah, I was pretty close with the 6, but it's 6.4. It's a little bit above. So if I can at least remember one of these formulas, I can graph this line. If I have a point off the line, say they want me to do a line perpendicular, I'd have to know this rule about the opposite reciprocal. But then all what I'd have to do if they gave me a point, say 6,4, and I know my slope is opposite reciprocal, I can use that same point slope formula. Again, here's my x1, y1, and just literally put in y minus 4, I'm going to need that, equals negative 5/2 parentheses x minus 6. There's the line perpendicular. If we had to write it in point slope form, we have the slope, but we may have to zoom out to find our y-intercept at 19. So then we could write our formula down, y equals negative 5/2 x plus 19. So hopefully you're seeing ways that you can work with perpendicular and parallel and slope and linear equations to help you solve these problems, even if you don't always remember the formulas. If you can graph points, you can find the slope of the line between them. If you can remember at least that perpendiculars are opposite reciprocals. Another way, if you can't exactly remember, is take a piece of paper up to your picture. So literally while you're sitting at your desk, you're given a piece of paper, right? And you'll have one of these lines, right? So let me come over here. If I maybe didn't know my perpendicular, I could plot the point I was given, the 4, 8 point, right? And I could take a square sheet, my piece of paper, and line it up, because isn't that going to give me a right angle? Now, could I find the slope? Could I count along here? It's a negative slope. So could I choose a point of interception and say, oh, that's going down 1, 2, 3, and over, but maybe it's going down a little bit further. Line it up a bit better. Maybe I could get close by just putting that piece of paper up there. If I forgot the slope, might even give me the idea of the slope. How do we calculate the slope? See that we're correct? That's the change in x over the change in y. So if I literally wish to calculate it, we've done it in Desmos, but since we're talking about it, again, it's the change in the y's over the change in the x's. So 8 minus 4 over 4 minus a negative 6. Remember how we got that 4 over 10? That's calculating. We got it just by counting. Graphing and counting. A problem like this gets into those systems of equations, which you love, right? You have to know several things. You have to know that when we have a parallelogram, and this you have to know, because it doesn't tell you on any sheets, the diagonals bisect one another. Now, a hint here, fold your paper. What do you notice about those diagonals? Literally take a piece of paper, fold it, because that's a parallelogram, right? And fold it and see if there's any congruencies in the diagonals, in the pieces of the diagonals. Because you can sit there and do that. Now, if we had to do this manually, we could say 4x minus 2 equals 3y minus 1, and 3y minus 3 equals 3x. We could take this and get it in terms of y by simply saying 3y equals 3x plus 3, divide the entire equation by 3, and that gives us y equals x plus 1. Now I can come back to my original formula, and wherever I see a y, I'm going to plug that in. So 4x minus 2 equals 3x plus 1 minus 1. And then I can solve. 4x minus 2 equals 3x plus 2x equals 4 through the subtraction property by subtracting 3x from both sides and the addition property adding 2 to each side. To find y, it equals x plus 1. That took a little bit of time and work. Your calculator will do this for you. Let's bring up Desmos and see how it could have helped us solve this problem. We do have to know the equality there. Can't get out of knowing that equality. So some things you do have to know. And like I said, sit there and fold a piece of paper to find out what the diagonals are doing. Is there an equality that you can use? That said, in your calculator, 4x minus 2 equals 3y minus 1, one equation. 3y minus 3 equals 3x. Where do they meet? Voila, isn't that what we just said? 4 and 5. The calculator, as long as you know to set this equality up, solved our equation for us, gave us the values for x and y for which this is a parallelogram, which is what we were asked to do. What if we have to reflect a point over a line? Sometimes we forget about these things. So again, we know that we can put a point out there. We can also put the line of reflection out there, y equals x. So now I have my point and my line. Which way does the point have to go? It has to go 90 degrees this way, right? Because it's going to reflect over the line. Maybe you can't remember those points. That's okay. What about that piece of paper again? We want to find it going over that line. Desmos is giving us that. You can get your handy dandy little sheet of paper out because you're given as much paper as you want, right? And we're going to come over here and we're going to put the paper like this and make it perpendicular to the line, right? Does that help you see that you're going to go -4 and up 3? Does that put you in the right direction? Of what we need to do? Hopefully it does, because these points literally flip-flop. But we do need to be 90 degrees to that point of reflection. And just seeing a piece of paper over there can really help if we've graphed our line and graphed our point. This video is a little long. Hopefully it's helpful, and I'll be following it up with a Google form so that you can practice a little bit more with the sheet and with the Ohio practice test, which I've just passed out to you, and hopefully you'll find helpful. Get used to using this Desmos calculator. This is the one that's on the test. It does have some limitations. And good luck on your test.